Hello everyone, I'm Pushpita Chandra. I'm a PhD student at IIT Delhi. I'm the TA for this session. So today I'm going to discuss something pri- uh, from very first few weeks of the classes, which is the matrix method. Method. So the matrix method. First, we need to know what is paraxial rays. So paraxial rays are the rays which are very close to the optic axis the of the system, like any lens. This is the optic axis or symmetric axis. The rays which make very small angle with the optic axis or very close to the symmetric axis, they are paraxial rays. Their angle theta is so small that we can assume that sine theta is proportional to theta and cos theta is almost 1. Okay, as we know that sine theta, when we expand it, so it becomes theta minus theta cubed by 3 factorial plus theta 5 by 5 factorial and so on. So when theta is so small, we only consider this theta, and similarly cos theta is 1 minus theta squared by 2 factorial plus theta to the power 4 by 4 factorial and so on. So we only consider this one. So just what is the paraxial place? So matrix method work in the paraxial approximation. Let's consider this is a mirror. So here it is a point. So the light coming from, or we can say we need to know the coordinate of this point. So to know that the coordinate of this point, we need three coordinates. Right? This is symmetry axis. Okay. This is x, height. Height from the symmetry axis we need to know. Okay. Refractive index we need to know. And the angle between this is the symmetry axis, but we can assume that in vector notation we know that if two vectors are parallel and have same magnitude, they are the same. So this is the symmetry axis, but if the ray is going like this or going like this, so how can we measure the angle? We will assume a parallel line of the symmetry axis from this point and measure the angle between this. So we can say it is alpha. So we need three coordinates. One, height from the symmetry axis. Second, angle between symmetry axis and ray. The third one is refractive index. So to reduce the three number of coordinates, we like assume another coordinate which is lambda. Lambda is a mixture of n, or you can say function of n and alpha. Okay, and this is sharp. So what is lambda? Lambda is n sine alpha. Okay, and we are using paraxial approximation. There comes the paraxial approximation. What is that? That sine alpha. Alpha is so small that sine alpha is equal to alpha. So lambda, we defined a new parameter lambda, which is a function of n and alpha, or you can say that n into alpha. So we get a new parameter lambda, which is a combination of two other parameters. So now we have two parameters, lambda and x. Okay. So this will make the job easy. Okay. So first we need to evaluate what is the translation matrix. Okay. So any ray traveling from a homogeneous medium of refractive index n0, which is initially at a distance x1, it is where it is x1, and after some time, which makes an angle alpha 1, this is alpha 1, the ray is traveling, and now the ray goes to a point where the distance between the axes is from the symmetry axis x2 and the angle is alpha 2. Okay. So we need to, like, we define the coordinates like this: lambda 1 x1, lambda 2 x2. Okay. We need to write lambda 2 x2 in terms of lambda 1 x1. Okay. Lambda 2 will be some function of lambda 1 and x1, same as x2 will be some function of lambda 1 of f1 or x1. Okay. So we need to find this matrix, and this matrix will be called translation matrix. Okay. So from the graph, I need to do. This is a mirror concave. Uh, So we don't need to go through that thing, that what is the mirror and this thing. Uh, Now first we are only concerned about like 2 point from A to B, the ray is traveling and we are ready to find the translation matrix. So here the coordinate is lambda 1 x1. So the medium doesn't change. Okay. So lambda 1 is n x1. Sorry, n alpha 1. Lambda 2 is n alpha 2. Okay. And this lambda 2 is 2. And for the translation, you can see that this is alpha 1 and this is alpha 2. From the geometry, it is like evident that alpha 1 is equal to alpha 2. Okay. So n is also the same, similar. So lambda 1 will be equal to lambda. Okay. And let me draw this clearly. Okay. So there is a point A, this is B. Or you can say that this is alpha. Okay. This is x1 and this is x2. So what will be the tan alpha? Tan alpha will be x2 minus x1 d, or you can say alpha 1. And due to paraxial approximation, we know that sine alpha is proportional to alpha, cos alpha is proportional almost equal to 1. So tan alpha is proportional to alpha. Okay. So alpha 1 is x2 minus x1 for d. So you can write x2 as d alpha 1 plus x1. Okay. You can write, but here we didn't count the refractive index change, right? So we can write this d by n into n alpha 1 plus x1. Or you can say that coordinates for lambda and x, here we are written alpha, we need to write it in terms of lambda, lambda 1 and x1. That's why we divide the d by n and multiply it into n. So it will be d by n like this. Lambda 1, lambda 2 is equal to lambda 1 and x2 is that. So we can write it in a matrix which will be like that. So lambda 2 is equal to lambda 1. Okay. X2 is equal to d by n lambda 1. So d by n will be over there and x1 is 1. So this is the translation matrix. So whenever ray go from one point A to B, the D is this distance, okay, or length. The translation matrix will be this. Right. So translation matrix is this thing 1 B by N 0 1. It transpose into 1. It's not equal to 1. So, but lambda is this is not an orthogonal matrix. Okay. Next, we need to like now obtain matrix for reflection. Okay. What will happen if there is a surface? So we assume a spherical surface. Okay. So here is a ray A, here is a ray B. So this is the surface, and due to refraction, direction will change. Let me draw a different direction, otherwise it will be confusing. Okay. This is N1, this is N2, this is alpha 1, this is alpha 2. Okay. So we will here there is a point, and after the refraction there is a point. From this point to that, this is pure translation, and this point to that, this is pure translation. For that, we need to use translation matrix. But beside, just before the surface and just after the surface, there is a refraction effect. So for that, we are like obtaining the refraction matrix. So just before the spherical surface and after the spherical surface, the distance from the symmetry axis is same, which is x. So we need to write lambda 2 and x2 as a function of lambda 1 and x1. So you can see that x2 is equal to x1. Right? Now we need to use the Snell's law. Okay. So Snell's law says n1 sine I is equal to n2 sine R. So here, what is the sine I? The whole thing is I. Okay. And this whole thing is R. So I is equal to, this is phi. And this is phi. So I is equal to, from here, this phi and this is whole thing is R. This is alpha 2 and this is phi. So I is I plus alpha 1. By geometry, we can prove that alpha, both phi are same, the same thing. And R is phi plus alpha 2. So paraxial layout approximation says that sine I is equal to I and sine R is equal to R. Okay. And this is called I is equal to phi plus alpha 1 and phi plus alpha 2. So n2 x2, okay, sorry, 2 alpha 2 is equal to n1 alpha 1 minus n2 minus n1 phi. Again, you can see tan phi is equal to x1 by r. Okay, and phi, the angle phi is also small. Model paraxial approximation. This is x1 r, which is equal to xr. Okay. So n2 alpha 2 is equal to n1 alpha 1 minus n2 minus n1 phi. Phi is equal to x by r. We cannot write the matrix in terms of phi. That's why we need to bring the x part. So this is lambda 2, this is lambda 1 minus, here we can plus or we can say the minus p to x1. Then what is p? P is n2 minus n1 by r. Okay. And x2 is already 0 into lambda 1 plus x1. So remember, P is n2 minus n1 by r. So whatever the matrix we write, we are writing the matrix P because like doesn't get cubperson, but you need to remember the what does it says or what does it mean P lambda 1 and x1. This is we will call R matrix total refraction. P is equal to n2 minus n1 R. Okay. So the P is called power of refracting surface. Okay. Now determinant of R is going to, okay, that is only for some, but R T R is not equal to I again. Sorry, I read one. I write, okay. Here I have written one, but it will not be one. It is I. Okay. Unity matrix, not unity. So now we'll discuss a case. What is a refraction through a spherical refracting surface, or we can say imaging by a spherical refracting surface. So, prior to that, I need to discuss that, excuse me, in general, optical system is made up of a series of components, lens, or mirrors, generally like that. Even if we use telescope and spectrometer and all those things, inside that, it's a combination of lens and mirrors, nothing else. So you need to divide a optical system in a small part where there is translation and refraction only, and combine them and get a matrix multiplication, which is which can be characterized by refraction and translation. Okay. So what happened? This is the optical system. Yes, array exists. This array has lambda 1 and x1. And this is lambda 2 and x2. Okay. So we need to find relation between these two coordinates. And here it will be a matrix, or called system matrix. So the system matrix should be like that, that determinant of S should be equal to 1. As we have seen, that determinant of T is 1, determinant of R 1. So whatever system matrix we write, it should have the determinant of 1. Okay. Now, going back to the topic I'm discussing, reflecting surface. Okay. Okay. And surface is a curve, spherical curve. So the ray is going from A to B. So B. We need to write a matrix. Okay. So what I have told in we need to divide the part and break down up to a point where the system is only a combination of translation and refraction. It's an easy system, so we can do it very easily. Okay, so from A, here I say A dash. This is pure translation, and then here we can say B dash. Between A dash and B dash, there is only refraction, and from B dash to B, it is again translation. So let us lambda 1 x1, lambda 1 dash x1 dash. This is lambda 2 dash x2 dash 2 x2. Okay, right? So again, one thing, like in matrix multiplication, order matter. So we will see from the point of view of B. So B will see the ray is coming from B dash. B dash is C. The ray is coming from A dash. A dash is seeing then ray is coming from A. So B, which has the coordinate B, will see it means the if a person was there at the point of B, what would he have been seeing? So it is lambda 2 x2. We need to write it from of lambda 2 dash x2 dash. So this is pure translation 0. You can write this distance as u, this distance as v. Here u and v are like d. D is the like translation matrix. We have achieved that translation matrix is 1, 0, d by n into 1. Here the distance here, that was d. So here the d is equal to v. So we can say that is v1 into 1. We are using U and V because at the preliminary optics lessons in class 11 or 12, we have used U and V and used some formula regarding this. V is basically the distance between the optical system and the point. Okay. Okay. So we need to write lambda 2 dash x2 dash in terms of lambda 1 dash x1 dash. So there is the refraction happens. So this will be minus p 0 1. We have we say. Then there is lambda 1 dash x 1 dash, which will be the form of lambda 1 x 1, which will be 1 0. So 1 0. And here is another thing. See, the notation, the like if you fixed a notation here, we have declared B is positive. So from the spherical surface to B is positive. So the opposite of it will be minus U. The distance is U, but the notation need to be maintained just like before. Okay, or you can say minus U. Okay, so this will be minus U and it will be N2 and it is N1. So now we can write lambda 2 x2 in terms of what? 1 0 v by n 2 1, then 1 minus p 0 1, then 1 0 minus u by n, sorry, this will be 1 into lambda 1 x1. Okay, this is 1. Chalo. And now we need to multiply it. This will give us 1 plus p u by n1 minus p minus u by n1 1 lambda 1 x1. Just wait for a minute. This is technical words. Okay. Will be become this is the matrix. Okay. Now condition. For an axial point object, say x1 and x2 both are equal to 0. So you can write lambda 2 as 1 plus p. We, remember p is the power of reflecting surface. P u by n1 lambda 1 plus minus p x1 x2 equal to v by n2 minus p by n1 plus p v lambda 1 plus 1 minus p v n2 x1. So when x1 is equal to x2 is equal to 0, this needs to be equal to 0. So v n2 minus u n1 equal to p v u n1 n2 is equal to 0. So from this we can write E1 so this becomes n2 by v minus n1 by 0 equal to p, which is n2 minus n1 by r. So we know this equation. Now the equation will become for the axial point. So this is equation 1, this is equation 2. Now equation 2 will become x2 is equal to 1 minus pv. Remember, all this condition is for axial point. For non-axial point, this all discussion is for axial point. For non-axial point, this lambda 2 x2 term, this equation 1 and 2 will define the system. But for axial point, equation 2 will become this. And for that, we will get lateral magnification is x2 by x1 will be 1 minus p v by n2, which is 1 minus v by n2, n2 minus n1 by r. And we have proved that n2 minus n1 by r is n2 by v minus n1 by u. So, which is m becomes v by u and 1 into. This is also a well-known equation. Okay. Now, we move to a topic, formation of image due to refraction. We are talking here about image, but we are only considering one ray. But remember, if we want to image a whole thing, the ray is coming from each point. So we need to consider each point, we will get an exact image. That's why we are calling it image. From system. So this is the optical system. It, this is the distance d1 minus, this is system, this is air, this is air, and this is d2. Now I have previously already told that this is a system matrix, which you can assume as B minus A minus B C. The mod of S should be equal to 1. So B C minus A D is equal to 1. Okay. Okay. So here A, B, C, and D, they are called Gaussian the matrix B minus A minus B and C is called Gaussian matrix. Okay. So like previous thing, we can the same procedure lambda 2 x2. It will come the last is first. Here is the translation. So the translation matrix will be here 1 0 2 2 1. D2 by 1 actually. Then the optical system matrix, which is B minus A minus B C. And then again in the minus D1 by 1. So we need to multiply. Okay, sorry. There is another thing. After all this multiplication, this term will be like this. 2b plus a d1 d2 minus b minus c d1 is minus a is minus a d2 plus c lambda 1 x1. Right? So again, assumption same as previous one for an axial point object. So let me write lambda 2 lambda 2 will be b plus a d1 lambda 1 minus a x1 x2 is b2b plus a d1 b2 minus d minus c d1 lambda 1 plus c minus b2a x1. Okay, so let them give the name, not I am to give them and 2. So the assumption is for axial point x2 is equal to x1 is equal to 0. It will be on axis. So this term will become 0, which is b plus a d1 d2 minus d minus c d1. This term will become 0. We can write this as b2b minus d plus d1 a d2 minus c is equal to 0. Okay. This is called image plane condition of axial point object. This thing. Let us give the name 3. And again, magnification is equal to x2 by x1. This point, so equation 2 becomes x2 is equal to c minus b2a x1. This is equation number 4. So it is c minus a b2. Okay. For action point, the system matrix will be so this is L, and determinant of L should be 1. First of all, I want to say that for optical system, I have keep it blank. There can be n number of lenses and mirrors in any formation. Uh, just need to put those matrices in a order and multiply them, and that will give this kind a matrix of this order. Okay, when we find something, we'll have some number and something. Minus a will equal to be something, b will equal to something. Then we can put directly into these equations. That's the point. They have been assumed like that. Some time you will be given those Gaussian elements or Gaussian matrix elements. So the mod of L should be 1. The mod of L is A B1 to C minus A B2, which is equal to 1. So it will be C minus A B2 is equal to 1 plus B 1 by B plus A D1. So n can be written as B plus 1 by B plus A D1 also. So that can be written as lambda T x3 as 1 by n minus a 0 n, sorry, I should not like that. Then is equal to 1 plus b plus a d 1. So this will be, and for inverted images, we normally use model. Okay. So now we move on to another like uh, example, I can say that example of the thing we have already obtained. That obtain an expression of system matrix. So we need to first obtain a system matrix. Okay. For a thick lens. This is the lens. Okay. So we need to obtain like the S for this. And the S only concerns the translation and refraction happening between these things. So say the ray is coming from that way, and this is given that way. This is like you can say this is minus T1, this is plus T2 and whatever kind of thing. But we are only concerned about this point. So first this point lambda1 x1, okay, and after the lens that is lambda2 x2. So what happened here? Two refraction here, lambda1 dash x1 dash, then translation whatever lambda2 dash x2 dash, then again reflection lambda2 x2. Okay, so and all matters. So we write lambda2 x2. First, first we'll write the refraction matrix for this refraction, then the translation matrix, then this refraction. Okay. So 1 minus 2, 0, 1, 1, 0, 1. Okay. The distance to here is T and refractive index is N. This will be Tn. Okay. P by N. 1 minus P1, 0, 1, lambda 1 x1. Okay, after all the calculation, this term will be 1 minus P2 P by N, T by N, P1, P2, P by N minus P1 minus P2, 1 minus T by N, P1, lambda 1, x1. So the Gaussian elements for the thick lens. We know is of the form like this. So A will be P1 plus P2 minus P1 P2 P by N. B is 1 minus P2 P by N. C is 1 minus P1 P by N. D is minus T by N. Okay. For thin lens, all we need to do is T tends to 0. So for thin lens, the Gaussian elements became A is equal to P1 plus P2, B and C is equal to P1, and D is equal to 0. So the system matrix for thin lens is nothing but 1 minus V1 plus V2 0 1. You remember this equation, right? Equation 3. So if we put these values in equation 3, which is B D 2 plus A D1 D2 minus C D1 minus B is equal to 0. For thin lens, get D2 into 1 plus, okay, sorry, minus 0 plus D1, D1 plus B2, D2 minus 1. After simplifying, we get 1 by D1 minus 1. 1 by D2 minus 1 by D1 is equal to D1 minus 1. Here, this optical system has effective index n, and outside the system, the effective index of air is 1. So n1 minus 1 by r1 plus 1 minus n by r2. So it will become n minus 1 by r1 minus 1 by r3. Okay, which is equal to 1 by f. So we got the equation we have known, which is 1 by d2 by minus 1 by d1, which is equal to 1 by f. That f is 1 by p1 plus p2, which is n minus 1, 1 by r1 minus 1 by r2 inverse. Okay. So for thin lens, the gain minus 1 by f 0 1. Okay. Now, signs of R1 and R2 for different types. So R1 will be greater than 0 and R2 will be less than 0. Because radius of curvature R1 is this side, so this is a positive side. But radius of curvature for R2 is this side, so this is negative side. That one, that is one. Then this, then for this is completely opposite. R1, then again radius of curvature will be on the left, which is less, minus, and R2 will be on the right, which is positive. Then this, where both are negatives. And for this lens, okay. Okay, an example. Suppose consider a plane convex lens having refractive index one point five. With convex surfaces, convex surface, so your radius of curvature of 3.5 centimeter and light incident on the convex surface. The center thickness of the lens is 0.6 centimeter. Construct the system matrix. Okay, so this is the thing. The light incident on the convex surface. So whatever we do in that, we need to construct only the system matrix. So first, for this, radius of curvature is 2.5 centimeter, or what? And R2 is infinity. Okay. So P1 is N2, where N2 is 1.5 minus 1. Now it is going by 2.5, which is 0.2 centimeter inverse, and P2 is 1 minus 1.5 infinity, equal to 0. So the system matrix will be then 7. Okay. Here R1 is positive. The system matrix would be first the refraction at this surface, plane surface. So this will be 1, 0, 0, 1. Then the T is here is given from 6 centimeter. So this is 1, 0, 0.6 by 1.5, 1, and then the last reflection. It would have like put this value in equation 1 and 2, you will get the same answer. But you don't need to remember all those calculation. After all the calculation, this become 1 minus 0.2, 0.4, 0.9. This is the system matrix. Can write this that way. Now, going further in the discussion, I want to discuss 3 pair of points in an optical system which we record greatly in the description of image formation. And these points are called cardinal points or Gaussian points. They are unit points or principal points. There are two unit points or principal points. An optical system has two middle points. Three is two focal points. Okay. So first unit points and also unit planes. Okay. So unit planes are the two planes, one in the object space and other is the image space. Let me clarify what is object space and image space. Like this is this optical system. The ray is coming from here and inside this something happens and the ray is there. The object is in here. So this is object space. And the image will form this side. So this is image space. Okay. So unit planes are two planes, one in the object space and the other is in the image space, such that the lateral magnification between the planes are unity. It means that one ray of light originating from the unit plane in the object space will image at the same height from the unit plane in the image space. Okay. Okay. Another thing. Here I have like discussed translation matrix and matrix for reflection. Matrix for reflection is like R injunctions are seen. Okay, sorry. But with as forces becomes 1, 0, 0. Because in reflection n2 minus n1 both are same. So that becomes same. So here we assume that is unit plane, the object space, and the second unit plane in the image space. So this distance, I have assumed that minus E1 is distance minus DU1 is distance DU2 is distance U2 or V. Let us call it V. So let's go to so from the discussion we have already obtained in the system thing, which is what? That C minus AD for optical system, that C minus A D2, here D2, we are assuming from unit plane to unit plane is the optical system. So here it will be D U2 is equal to 1 by A plus AD1. Okay? Is equal to 1 because magnification is 1. So DU1 becomes 1 minus B by A and DU2 becomes C minus 1 by A. Okay? And U is the distance of the object from first unit plane. Object or object plane. Object plane is a plane which contains the object. And V is the distance between image from the second unit plane. So we obtain V1 to be U plus D U1. So D1 is the distance between the optical system to the object. So here the distance between optical system to the object is distance between first unit plane to the optical system and first unit plane to the object, the combination of two. Similarly, D2 will be P plus DE2. Okay. So from the equation number 3, let me write the equation again. The equation number 3 was D2B minus D plus D1 AD2 minus C equal to 0. This is image plane condition. Okay. From that, we can obtain D2 is D plus C D1 B plus A D1. So D1 is basically okay, so and we also have obtained what is DE1 and DE2. So this is E plus 1 minus B A. This is B plus C minus 1 by A. So D2 is V plus C minus 1 by A is equal to D plus C D1 Here also we need to put the value of d1. C into u plus 1 minus u by v, b plus a, u plus 1 minus k. So from this, we got V is equal to A U A 1 plus A U. Okay. Then we use the condition that BC minus AD is equal to 1. So from this equation, when we simplify, we get 1 by U is equal to A. Okay. Now, find the position of unit lengths for a thick lens. Assume it is equiconvex. For a thick lens, we know this P1 plus P2 minus P1 P2 P by N, P1 minus P2 T by N, C1 minus P1 T by N, B is equal to minus T by N. So this is a thick lens. This is one here defective index in N. So R1 mod of R2 is same, which is can be written as R. So P1 will be N minus 1 by R. P2 will be 1 minus N minus R, which is N minus 1 by R. So P1 is equal to P2. So DU1 becomes 1 minus B by A. We need to find the unit length. So DU1, which is 1 minus B by A, will be 1 minus P2 T by N, P1 plus P2 minus P1 P2 T by N. And P2 will be C1 minus A. And which will be 1 minus P2 T by N minus 1 plus P2 minus P1 P2 T by N. Okay. So let me show you one calculation, which is 1 minus 1 minus P2 T by N, P1 plus P2 minus P1 P2 T by N. We can write it as a Pt by 2 into 1 P 1 minus Pt by 2. Okay. So this P will cancel, so it will be T by 2. 1 minus T into N minus 1 2 R N. Then we get the value of P inverse. If radius of curvature is greater than the thickness of the length, so r is greater than t. So t by r is less than 1. And again, n minus n is less than 2n. So n minus 1 by 2n is less than 1. So t n minus 1 by 2n r is less than 1. So 1 minus t n minus 1 by 2 r n is equivalent to 1. So d in 1 becomes t by 2n. And d in 2 becomes minus t by 2n. And this is the position of the unit length for equiconvex lens. And generally for thin lens t is equal to 0, then nodal unit planes is at point 0. So now back to the second point, portion cardinal point, which is nodal point. So the nodal points or nodal plane are the points when the relative angular magnification between them is unity. There, which is for unit plane, the magnification was lateral magnification was 1. Let me write that. So let us assume that this is the way, this is also the way. This is alpha 1, this is alpha 2, alpha 1 is equal to alpha 2. So M, the relative magnification is equal to 10 alpha 2 by 10 alpha 1, which is alpha 2 by alpha 1. And this is equal to 1. This is the relative lateral magnification here. So now we need to know the position of the nodal points. Okay. So to know the position of the nodal points, we consider this equation that lambda 2 can be written as b plus a d1 lambda 1 minus a x1 from this equation. So lambda 2, because we are talking about angle and lambda 2 only contains the angle, because lambda 2 is n to lambda alpha 2. Here the ray goes from ear to the lens and comes out of the I should not say lens because it can be any optical system. So this n, not n1 and n2, n alpha 2 and n alpha 1. So for axial point x1 equal to 0, lambda 2 becomes lambda 1 b plus a b1 So lambda 1 is equal to n alpha 1, lambda 2 is equal to n alpha 2. So alpha 2 is equal to alpha 1. So lambda 1 is equal to lambda 2. That's mean d plus a d1, where d1 is what? The d1 is the distance, but here the object to have a lateral magnification 1, it has to be in nodal plane. So d1 becomes dn1 is equal to 1. So dn1 become 1 by b, 1 minus b by a, which is we know d is 1. Similarly, dn2 can say is equal to b. So basically, we can conclude that nodal planes coincide with the unit plane, if only if the incident and emergent medium are identical. Nodal plane which is perpendicular to the principal axis and contain the nodal plane, nodal points or unit plane points are called unit plane and nodal plane respectively. The third is focal point. There is first focal point concept and second focal point. First focal point is the position of the object. Whose image will form at infinity. Second focal point is the position of the image. Whose object is at infinity. Okay. For that, we know that d2 is equal to b plus cd1 by b plus ad1. Okay. So d1 first focal point and d2 is infinity and d1 or df1 becomes minus b by a. And when we call d2 is df2, then d1 is equal to infinity and d2 is equal to df2 becomes c by a. Okay. Now quickly discuss some points. Problems. So problem 1. Consider a thick equiconvex lens M is equal to 1.5 having radius curvature 4 centimeter, center thickness of the lens is 1 centimeter and the lens is placed in air. Obtain the system matrix and position of cardinal points. So a thick equiconvex lens T is equal to 1 centimeter. So the system matrix will be at the last refraction at the last surface of the translation 10 t by n 1 and 1 minus p1 0 1 lambda 1 x1. So p1 will be 1.5 minus 1 by 4. Okay, and p2 will be the same. Because it will be 1 minus 1.5 minus 4. So the system matrix will be 1 minus 0.12501 by 101 by 1.51 into sen 1 minus 0.125 this kind of thing, and after calculation it will become 0.92967 minus 0.24 0.92. Okay, so B will be 0.92, A will be 0.24, D will be minus 0.67, and C will be 0.92. Now we need to know the cardinal points. So the focal point, the unit plane and nodal points are the same, which is D1, D2 by D1 or Dn2, 1 minus B by A, which will be 0.34. 0.92 minus 1 by 0.24, which will be minus 0.34. Df1 will be minus B by A, which will be minus 3.83, and Df2 will be C by A, which will be 3.833. Problem number 2. Consider a sphere of radius 20 centimeter containing a material of refractive index 1.6. Find the position paraxial focal points and unit lengths. So we know the system matrix for thick lens is 1 minus P2 T by N, T by n, P1, P2, P by n minus P1 minus P2, 1 minus T by n, P1. Okay, now the catch is T is 40 centimeter because it is sphere. 20, 20, 40 centimeter, and n is given 1.6. Good. P1 is 1.6. So P1 will be 1.6 minus 1 by 20, which is 0.03. And P2 will be 1 minus 1.6 by minus 20, it will be 0.0. You put this value, you will get the system matrix. Matrix which will be 0.25 minus 0.0375, 25.25. Now, the focal point BF1 is equal to minus B by A, which is 0.35. A is 0.0375. And DF2 is equal to C by A, which is 0.25 by 0.0375. And DU1 into 1 minus B by A, took the value 0.75 by 0.0375, which is 20. DU2 is 1 by A, which is 0.25 minus 1, 0.0375, which is minus 2. Next problem. Find the system matrix of a thin lens in terms of focal length. We have already done that, which will be the system matrix for thin lens is 1, P1 plus P2, 0, 1. And P1 plus P2 is equal to minus 1 by F. Okay. So system matrix will be minus 1 by F, 0. When it comes in a question, we need to be start from first. Then problem 4. Find the system matrix for the combined lens. There is a lens, they are all thin lens. And this is a lens. This has a focal length f1, this has focal length f2, and their distance is t. So what will be the system length? First, system length for the concave lens, 1 by f2, 0, 1. Then the translation matrix 1, 0, 3, 1, which is in air. Then the focal length 1 by f1 focal length for reconvex glass. So it will become 1 minus t by f2, t f1 f2 minus 1 by f1 minus 1 by f2, t1 minus t by f1. Okay. So for combined lens, A is equal to 1 by f1 plus 1 by f2 minus E f1 f2, which is actually, we know, plus the for any length system it is 1 by f01. So here 1 by focal length for the combined system is this. So this is 1 by f1 plus 1 by f2 minus t 1 by f1 f2. So this is the focal length. Focal length for the combined system 1 by f is this. And you cannot really find the position of unit length and focal lengths. So problem number 5. Suppose that the focal length of a convex lens f1 is equal to 50 centimeter, concave lens f2 is equal to 20 centimeter, and separation between them is equal to 25 centimeter. So determine the system matrix. And position of unit lengths. This is same as the S will be 1 plus 25 by 20 minus 25, 50 into 20 minus 1 by 50 plus 1 by 20. 25 1 minus 25 by 50. And this is will become 2.25 25 5 into 10 to the power minus 3.5. We can obtain the length, but if the question get extended by that for an object of height 1 centimeter placed at a distance 27.5 centimeter left from convex lens, determine the size and position. Then what you need to do is put the values in B2, which is B plus C D1 and B plus A D1, and put the value D1 is minus 27.5. The value of this B is minus 25 plus C is 0.5 into minus 27.5. B is 2.25 plus A is minus 5 into 10 to the power minus 3 into minus 27.5. This will be the value, and magnification is 1 by B plus A D1. So 1 by 2.25 plus A is minus 5 into 10 to the power minus into B1 is minus 27.5. This will be the value. So this will be 2.25 and 0.005 into 27.5 will be 0.1375 plus 2.25. Okay, so 1 by 2.3875 and by 2.3875 is 0.4. So that is for today. We will meet the next class.